Hey guys, I'm going to give a quick demonstration of what Kura is, and then at the same time I'll walk through some of the code that we're having over here. So on a high level, what Kura allows you to do is take Claude conversations, and from there extract some general insights. So I have some general usage stats over here, cumulative words, messages per chat. What's really useful is that you can basically see on a high level what are the clusters that you have. So over here you can see that a large cluster that I have is to improve code, build applications, and troubleshoot technical issues. And this is a description. So for every single cluster, we have a title, description, and we have all the chat IDs that make this up. And then you can slowly reduce them to smaller and smaller clusters from there. What's really nice is that you also have a little map view over here, which allows you to explore clusters that are basically the embeddings itself, and we cast it down to a two-dimensional space using UMap and HTTP scan. So you can see that as we go lower and lower into the clusters, so starting from the root clusters and moving downwards, we start to see a larger number of clusters. For example, over here, a lot of it is basically tech-related, technical documentation, configuration files. This is explaining investment strategies in Python code. This is about mental health relationships, improving skin and hair care. And as you go deeper and deeper into the cluster, you can start to see a lot of these individual classes start to form, and you can explore any of them at any point in time. So this is fully available in the source code itself on GitHub. So now that we've done so, let me just walk through some of the code that we're working on and how this works. So the way that we want to start is we can look at the Kura class itself. So we have a whole bunch of different things. So we have on a high level, we have the embedding model, which we use to embed the cluster descriptions, the original conversation summary, the high-level clusters itself. We have a summarization model that takes a user conversation and summarizes it. We have a cluster model which takes a bunch of individual summaries. So these are conversations themselves that are summarized so that we can extract general usage patterns. And then we cluster them using in this case, we're just using simple k-means, but you can, at some point, you should be able to throw in whatever you want. You can see over here the method is just defined as a base clustering method. You have a meta cluster model that takes individual list of clusters and then converts them to a smaller list of higher order clusters. And the way to think about it is that, let's say you had a bunch of larger clusters which were rewriting React components, writing Python asynchronous code, debugging Rust asynchronous and concurrency issues. Or you could create a meta cluster that essentially is, that describes all this, where a user was really asking for help with regards to implementing code that dealt with concurrency issues in languages like Python, Rust, and specifically he was using a set of frameworks like React. You can sort of tune that according to the prompt. And so the way to think about it is really that we have these, let me just pull it up. The way to think about it is that we have a summarization step at the start, we have a base clustering step, and we have hierarchical clusters and we just keep repeating this until we get a desired number of clusters. The original Anthropic paper just embedded the individual clusters summaries and then a cluster using a k-means, and where k is basically a function of the number of average items that they want per cluster. They didn't release that, but that's how I've done it in the implementation itself. And so you can see that basically the API is incredibly simple. You just initiate Kura, you just load the conversations itself. These are Claude conversations. And so they look something like this, where you have a UID, you have a name, you have created, these are just timestamps, account, the chat messages here. We only extract out the content type equals text, basically. So that is basically how Kura works on a high level. And so we're going to skip over the front end itself because it's not really interesting. And what we're going to be going through is each of the individual portions and these individual classes and what they do. All right, so we've gone through basically the high level idea of Kura, some of the base classes, and so we'll look through each of these steps in detail. So we're going to start with the summarization step. So this isn't anything fancy. Basically, all we do is we ask for the language model itself to generate a description of the task. So for example, this is mostly pulled from the Anthropic paper, where you say the user's overall request for the assistant is to help implement a React component to display a paginated list of users from a database, or the user's overall request for the assistant is to design and architect a REST API for a social media application. And these are very, very short sentences and at most like 30 words. And so the reason for this is that it's basically able to redact a lot of PII, and so for Anthropic, that's a huge thing for them. Um, I think they've done some evaluations where you can remove about 85%, 98.5% about a lot of the PI that they identified. And so essentially why this is useful is because by generating a general summary that doesn't focus on specifics like, oh, the user is someone living in Singapore, like me, who is a certain age, lives in a specific neighborhood. It's just saying that, hey, this person is asking for help implementing React. So instead of me saying, hey, it's raining in Tokyo today. I am headed to Shibuya later to go into the office. I need some work. I'm wearing some Doc Martens. Um, is it a good weather? Should I bring an umbrella? Instead of being bogged down in a whole bunch of these details, we can transform that as something that says that the user's overall request for the assistant is to help give some suggestions on what to wear and to prepare given the certain weather conditions in the country he's in. Right, and so you can see how the high level summary of what the overall conversation goals are, and that's kind of why Clio is really interesting in this sense. One thing that I know that Kura doesn't exactly implement yet is that we don't have this idea of hooks. And so for you, if you are building, let's say, a coding agent or some sort of language model application that cares about specific domains, you could be extracting certain things out. Right, for example, in that specific conversation, we could care about, hey, the user's talking about things like Doc Martens, the user lives in Japan. Yeah, and so I think the idea is that you want to have this customizability because you can sort of evaluate the hooks that, based on what you're extracting from the conversation itself. Also, I found that it was much more useful to put the conversation here inside the system prompt itself rather than to give it actual messages over here because then the language model was sort of aware that it wasn't a conversation that it was having but context that it should refer to rather. So that was the conversation summary itself. So that's the first step in Kura. We summarize all the conversations, so we get back what's called a conversation summary. So that is just this. It's a chat ID that we can link back to get the original chat, a summary, and then some metadata that we care about. Right. So once you've done that, we do a clustering itself. So that's implemented over here in cluster.py, where basically what we're doing is the specific method is generate cluster summaries. So what we do is we embed each of the individual summaries itself. So recall just now we had user conversations and we basically summarize the general user intent. And from there, what we're going to do is we're going to embed that intent. So we're going to take a user task summary, like the user is asking for help implementing a paginated list of components in React. It converts that into a summary itself, to embedding, and then from there we cluster using just simple k-means. That's all this is using. Once you've done so, we basically get a mapping of individual conversation summaries that are clustered together, like cluster 1, cluster 2, cluster 3. And what I found really interesting in the Clio paper was that they basically asked the model itself to generate a precise name, given a bunch of related statements. In this case, those are the user intents. Create a concise summary that captures the essence of the statements and distinguishes them from other similar groups, right? And what they want is a precise 2-sentence description and a title. And one of the things that they really try to elicit here is that you want to make sure it's very clear and descriptive, and to identify and describe things that even if they're socially harmful or suggestive and sensitive. And so they will provide both positive examples and contrastive examples that allow the model to see with a bit more granularity into what these clusters should be. And these form basically the base clusters that we're talking about just now. If you look at the front-end demo itself, those were the lowest layer. That would be layer 4, 5, where we had a lot of clusters, and that's where we start with. Once you've done this initial generation of clusters, we get a list of clusters and we return it. So this moves us to the next step, which is reduce clusters. At this point, this is a bit complex, so to bear with me at this point. So what we're doing is an iterative process. So the way to think about the clusters is that they're hierarchical. So you have an initial list of base clusters that we have from the conversations. We created a bunch of base clusters. And our goal is to keep combining them into larger and larger, into smaller and smaller lists of groups as we go up the levels, so that we can essentially have a certain number of minimum clusters that we care about. So the way we do that is it's a tree method. It's a three-step process for each of these individual clusters. So let me just try to walk you through that now. This is implemented in the meta cluster method. So let's scroll down to this generate meta cluster method, which is called in reuse clusters. So there's a small edge case here, which is that if by some twist of fate the cluster is a size of 1, we pass it up, and this tends to happen if you have very small amounts of data, and so you have clusters that don't really sort of coalesce together nicely, and sometimes you have clusters where there's only one single cluster. That kind of gets solved in the next level itself, but sometimes it gets stuck in an initial local minimum and it just doesn't get combined up. And that kind of is the problem with something like k-means. So when it comes to the clusters themselves, what we do is we embed the name and description, and that gives us an initial embedding which describes what the cluster is doing. Once we've done so, then we essentially do this mapping over here. This is a very common method where we just set the item that we care about, the embedding that we want to use to cluster it, and that's because in the implementation of the k-means that I have, it sort of splits this data up. It does the clustering and then it matches it back again. So that's why it's done this way. There's no special reason. So once you have this initial clusters, what you have are the base clusters that initially, let's say you had 20 of them. You might now have 4 new groups, one which has 8, one which has 2, one which has like 5. And so you have these like smaller cluster groups. And this is where it got a bit more complex to implement. So what you essentially have is, this is going to be inside this is cluster. You want to be in meta cluster.py. Generate meta clusters. It's a three-step process. And so the first step is given, let's say, 10 candidate clusters, which are the 10 base clusters that you might start with, or a small list of higher level meta clusters you want to reduce. Essentially, what you want to do is you want to generate new names that you can do that cover like one or more of these clusters. In the original Anthropic paper, they allowed the model to generate anywhere from half the number of, let's say like we had n candidate class, n like cluster that we want to reduce. The model can generate anywhere from 0.5 to 1.5 candidate clusters, and then they then label the clusters again. I found that a really reliable way was just to cut the number of candidate clusters and just to give about half of them. And then from here, you basically generate these new labels and you label each of your original clusters with them. And so what that means is that your original clusters are now clustered together again. Right? There's a smaller, like let's say you had 10 to start with, and now maybe 4, the first 4 have the same cluster, new label, the next 2 have the same label, the next 1 has the same label, a different label, and so you have like these smaller clusters of clusters. And then you basically do a renaming of them. And so you just give it all of the cluster names and descriptions. You can see it over here. And then we generate a new description, a new title for this cluster, and that kind of describes and summarizes everything itself. And then we do that, and then we basically just save a checkpoint, and that kind of is what happens at the combination step. And so we keep iteratively continuing to do this until we have a list of desired top level clusters. Where I've set it to about 10. That seems to roughly be a sweet spot. For about 95 clusters, it takes about 3 steps to get to that, 3 to 4 steps on average. Once you've done so, I just use a dimensionality reduction technique called a HTTP scan and UMap. And so what we do is we essentially just embed all of the final clusters that we have, and we just run the HTTP scan and UMap on that whole list of clusters. And the way I was thinking about it was just that if you did the HTTP scan on a single layer one by one, it would be very local. But if you did it on the entire span of these individual clusters, you can start to see like patterns forming, and it would be more uniform, the parent clusters and the child clusters in a sense. And I tried to use the anthropic parameters, which are n components being 2, minimum neighbors being 15, minimum distance 0, and cosine metric to do that UMap projection. So once you've done so, everything is saved into a what I call a projected cluster, which is a unique cluster ID, a name, a description, chat IDs that make up this cluster, the parent ID if it has one. You have an x coordinate and y coordinate, and you have a level, which is essentially just the specific level that this thing is. But I do that resolution on the front end. It's a bug I need to fix. Um, so yeah, that's basically what Kura does. You have conversations that are summarized. Summaries are then clustered together to form base clusters, and these clusters are then recursively combined and labeled by language models to create new higher level clusters that combine the general sense of what these individual portions are. And from there, you essentially have this hierarchy of clusters that can basically describe and give you rough intent of what users are asking. And from there, you can also start to add in additional hooks, which can extract things you care about. And so if you're building any sort of B2B SaaS, let's say you might care about conversion rates, you might care about who's the party speaking, you can care about, let's say, feedback that users give. These are bits of metadata that you can hook on if you have the chat ID to link it back to. And so I think that concludes my technical deep dive for now. Yeah.